Now it's time to resume the session. Please come to the main hall. Can I ask you to be seated now?
Sure.
Okay. You have to press.
Tell me when I come.
Please come back to the main hall.
I will give you. Oh, it's under control.
Okay. I told them I think we can start. Okay, now there is a session on Boolean function and symmetric cryptography, and this will be chaired by Professor Cyril Mesnager from Paris 8, and I leave the floor to you.
Thank you so much. Welcome to this session of the afternoon of the second day of the conference. It is my great pleasure to introduce the keynote speaker, Svetlana Nikova. She's one of the highest and famous research expert in working in the research group of the group of COSIC in the electrical engineering of the Department of the University of Leuven in Belgium. She's an expert in security implementation. She worked a lot in from the software and hardware part of cryptography, specifically symmetric cryptography, and she has an important look at the advance in design, but also in attacks, and specifically, side channel attacks, and those all physical attacks that which are very, very important, specifically nowadays. So it's my great pleasure to introduce you. So please, it's
Thank you.
It's up to you. Thank you.
Do you hear me? Is it on? Okay. Thank you very much for the long and very nice introduction. And thank you very much for the invitation to the organizers of this very nice event. I'm going to talk about side channel attacks, physical attacks, not only side channel, but physical attacks, not about the attacks, but about protecting against these attacks, hardware and software implementations. And I'll mainly talk about a methodology that we developed with Vincent Ryman some years ago, called threshold implementation, which by now is one of the most used techniques to protect against side channel attacks. This talk is a collection of recent results by people from our group, our students and postdocs, so I'm using also slides of people that gave me. So this is the short outline. I'll introduce what physical attacks are, because I'm not sure how much you know about them. I'll just briefly introduce them, so if you know about it, I'm sorry, I'll be quick. Then I'll talk about TI, or threshold implementation, as a hardware countermeasure against side channels. I'll briefly talk about some challenges that we still face when we protect ASIC implementations. And then I'll talk about securing software implementations with masking, which is a very new topic. And then I hope I have time to talk a little bit about combined attacks, which is also a very new topic, and not much research is done there. So, let's start with the introduction. So far, what you heard most of the time, it was in this setting, in the black box setting, where you have plain text, ciphertext, and a key, but that the attacker is not allowed to look into this black box into the engine that computes, that performs a cryptographic computation, the attacker can only have either the plain text or the ciphertext, and then try to figure out the key by either breaking the algorithm or doing something else. But nowadays you have all these IoT devices which are in your pockets, and the attacker also can have them and can access them easily and can perform all kind of other attacks on them, either by just passively listening and collecting information about what, for example, power consumption the device has while doing cryptographic computations, or even more invasively by faulting certain values and then observing what the result is. So this is the so-called gray box setting, and these are the physical attacks that I will talk about. Of course, this has been, strangely enough, only discovered in the 90s, and we believe this is because cryptographers didn't talk too much to engineers. They didn't know about a lot of artifacts in hardware and software that are present, and then our algorithms don't take them into account. And since then, there is a whole new community, the so-called chess community, which looks at different attacks and countermeasures. And there is a taxonomy already of all these physical attacks. Mainly, they are passive and active. The passive are the side channel attacks, where the adversary is only allowed to observe and infer. And the actives are the fault attacks, where the adversary can do all kinds of invasive attacks. They can be semi-invasive or non-invasive or very invasive, depending on how much access he has to the device that he is attacking. When we talk about passive attacks, just very briefly how this works. The most famous or the most often used attack is the differential power analysis. And what the adversary does when doing differential power analysis is, so it's collecting a lot of traces, we call it. He actually exploits the data dependency of the power consumption and of the crypto device. And then he uses a large number of those traces and analyzes them with certain statistical techniques, statistical functions. And at the end, he gets this graphic that you see here, and every pick that he sees, which stands out of the rest, gives him information about the key. So it turned out unprotected implementation can be very easily attacked with such attacks, especially for public key cryptography. It's even simple power analysis is enough. On the other side, the active attacks use all kind of machinery that actually exploits weaknesses of the, makes the device work not in the way that it's supposed to work, either by doing some glow glitching or putting it in a temperature chamber or using a laser. So as I said, these are active attacks. And of course, devices malfunction sometimes. You get a blue screen on your computer, or the hardware doesn't work as it is supposed to work. And these are errors that are caused by a fault. And if you make the fault yourself, you can exploit this fault and then get the key out of it. How can you do that? As I said, you can make the device malfunction. You make it, what does it mean? You have to make it operate outside the intended specification. So if a device is made to work, for example, on 32 megahertz, if you put it on 64 or 100 megahertz, of course it will not work correctly. Something will get wrong. And then these are the global faults, like we call them, because they are not precise. They are on the whole computation, and they usually affect the longest critical path. You can do different things. You can do underpowering, which is lowering the supply voltage of the target device throughout the whole computation process. And then you can have voltage glitches. You can have clock glitches, which is, for example, the clock period becomes too short to allow a full propagation and stabilization of the correct result. Or you can do voltage glitches, which is higher propagation of delay in transistors. And these are all physical effects that engineers and hardware engineers know very well, and they are present in the devices if you know how to trigger them. You can also have more invasive and more precise fault attacks, which are fault injection, either laser or EM. Then you can be really very precise. You can choose which clock cycle to attack, and you can even have even more power. So what can you do? How does a fault attack work? What the attacker do is the following. He is asking for a cryptographic computation twice. The first time with the correct input and output, which is with the correct input and without any fault, which is his reference computation, and then with the same input, he injects a fault, and then he sees what happens, and then uses some kind of differential, like in the differential cryptanalysis analysis, and then he can derive the key. And sometimes, as I said, for asymmetric crypto, it's enough to have only one injection. For symmetric crypto, it's a bit different. And this is, of course, repeated many times. And then, based on this, the key can be recovered. So what do we do about this? Of course, after the discovering of all these attacks, the community started thinking of countermeasures against them. I'll start with side channel attacks first. So masking is the most used methodology to protect against side channels. It has been discovered long ago, almost right after the attacks were discovered. And the basic idea is the main goal is actually to remove the correlation between the secret key and the process data. What do? We split the data in shares, we operate on these shares, and then we only compute the final result at the end. And to compute, for example, a function f of x, we split x to x1 plus x2. This is the most simple case. And you can think of this being x1 to be a one-time path encryption of x with a key x2. And then y can be recovered from y1 and y2 because this is a secret sharing with two shares. So even if the adversary compromises an entire part of the chip, this function f1 of x1, there will be no sensitive data leaked because he needs the other part of the chip in order to get the full information. Of course, this is our mathematical representation of the reality, and what we do is we create models that we try to link with reality. Of course, they are never completely the same as what happens in reality, but we have to have a tool in our hands to design these protection schemes. And the most famous model is the so-called probing model, probing security, where you have d props independent, a set of d props independent of x. So out of d plus 1 shares, you are allowed to probe d. Just to make a link with something that you know, MPC, it looks very much like MPC, of course, and it actually comes from there. From what you call in MPC semi-honest or passive adversary corresponds to the side channel adversary in the physical world, and what you call active adversaries in MPC world corresponds to the fault injection attacks or adversary. So you can have different models, as I said. You can have probing in a specific wire, and of course you limit the amount of wires that you allow the adversary to probe. And the number of probes that the attacker can use is the order of the attack. So if you can only probe one wire, we have first order attack. If you can probe 2 wires, then we have second order attack. And this corresponds to the statistical moment that is used by the attacker to manipulate the traces that are collected. You can also allow the attacker not to only probe wires, but an entire part of the chip, including registers, memory, whatever is there. Then you have the tiles and probe model. So in the 2005, I think, there was a paper who actually showed that all the masking schemes that were available by that time were broken when we consider hardware implementations, because there is this phenomenon called glitches, which means, which is actually the effect of, effect of the hardware that is unavoidable. And sometimes, and then it comes from the fact that sometimes signal do not switch like we expect to switch from 0 to 1. And instead, some are switching faster than others, and there are some delays, some different combinatorial paths, unexpected spikes, which causes power consumption, and the power consumption of the CMOS technology actually very much depends on these glitches. So this actually makes the hardware work not as expected. And even if you have sharing, you have masking, it could affect the way the masking is done, and it could cancel out actually this masks that you add into the computation. So this has been discovered that actually the sharing, the masking don't work. And then in 2006, we proposed this other way of doing this masking in a way that the diversity cannot have a disadvantage, even when glitches are present. First, it was for first order DPA only. Then we extended it to any security order. Then we have, of course, tried to work on the efficiency and to use the minimum number of shares. And nowadays it is believed that it is proven actually that one of the properties, the main properties of TI, which is non-completeness, is a necessary property for every masking scheme. And here it is how it's quite a simple construction. You have three important properties. The first, of course, is correctness when you share it. And then the second and the most important is non-completeness, which means that all these component functions that you see in the middle, they should not depend on all shares. They should at least be independent of one share. And you can see, for example, S1 has no arrow from X1, Y1, Z1 from the first share. X2 does not depend on the second share, and so on and so on. And then the third property is uniformity, which is basically we should preserve the bias which is present in the joint distribution of the input shares before the sharing and after the sharing. So if it's a bijective function, before we share it, it should remain bijective after sharing it. And in this way, the power consumption of each component function is independent of X, and which means that the average power consumption also will be independent of X, which actually doesn't give the attacker any information about the share. So, because we have n out of n sharing scheme. How do we do this in practice? Here is a simple example of multiplier. Let's assume we have this multiplier with two shares, with three shares, sorry. And then this is a correct way of sharing it. As you can see, in each of the Z1, Z2, Z3, there is one share which is missing. And this is a correct non-completeness non-complete sharing. While if we make a mistake and we have one place where all the shares are present, this is already non-complete, and then the attacker already has all the shares of this specific input, and then it will not work the countermeasure as it's supposed to. Of course, this was for the first order. Now for higher order security. So for the first order, we said every component function should be independent of at least one share. When you talk about DIT order, we say that any combination of up to D component functions must be independent of at least one input share. This becomes, of course, much more complex, and the higher order, the more complex. Also, a property of this, after fact maybe, of this higher order threshold implementation is that you have different input and output shares. For first order, you have input and output shares the same number. While here, you have a so-called expansion. So if you have SIN, which is minimum TD plus 1 input shares, T is the algebraic degree of the function, D is the order, then the input shares are lower bounded by this number, which is here in the theorem. We also have later made another variation of TI, which is not requiring TD plus 1, but only D plus 1 shares, which is well less, especially for functions with higher algebraic degree. They also, in this case, they also have expansion. Then the input shares, if they are D plus 1, then the output shares will be D plus 1 to the power T. Here is an example for higher order non-completeness. Of course, here becomes much more messy than before, because you have to check all the possible combinations if they don't depend on at least one share. And you can see this is TD plus 1 TI, second order secure multiplier. You have 5 input and 7 output shares. And then you have to, of course, check all these combinations. Of course, this is simple when it's with a few shares, but if it becomes, if it's AES, for example, it becomes a bit messy. So for this to check, we have developed a tool which takes the implementation, the net list of the implementation, and checks if the non-completeness is satisfied. Because if it's not satisfied, it will definitely leak when you test it in the lab. Then this is another example with D plus 1 TI. You also have to have so you have here 3 input and 9 output shares. The output is reshared and stored in registers. And then the compressing phase is reducing the numbers to the shares. So you always have expansion first, register, and then the compressing coming back to smaller number of shares. As I said, non-completeness is a necessary requirement for secure masked implementations. First order non-completeness and uniformity imply first order composable probing security in presence of glitches. And did order non-completeness and uniformity imply did order univariate security in presence of glitches. How do we find these sharings? That's the next question, of course. Okay, we have these properties, but do they exist? Is there any generic construction? How do we find it's actually a Boolean function problem after all. So there was actually no generic construction until recently. We have also this classification. So first of all, TI is preserved under affine equivalence. So there's 302 affine equivalent classes, for example, for 4-bit permutations. We have tested in all of them, and then we classified them with how many shares which class can be shared in a TI fashion. The same was done for 5-bit permutations and for 6-bit permutations, but the bigger permutation is the more difficult the exhaustive search becomes, because that's what we were doing. When you implement an S-box, for example, the AES X-box, it's not efficient if you do it directly, because you know, it's with algebraic degree 7, so you would have minimum 8 shares, which is blowing up a lot the area. Of course, when we do hardware implementations, we do a nice mathematics, but we also want to have efficiency and something that is practical, and then people can put it in actually on a chip or on FPGA. So what we do is we use the Canwright representation of the S-box, and then we go, we use the subfield, we go to subfields, and we go down to from GF2 to the A to GF4 and to the 2, and then the smaller the field, the easier it becomes. And of course, the main problem, the main difficulties is in the nonlinear function. The linear functions are very easy, but the nonlinear functions are always a problem. So as I said, the main problem is also, of course, you have to make it secure, but you also have to make it reasonably big and reasonably slow and reasonably with a reasonable latency. So, and the problem is that all these requirements are contradicting each other. You cannot have everything at once. You have to make some trade-offs. And so what we usually do is we optimize on one of them, depending on the application, and then we sacrifice a little bit the others. The main area for now is kind of okay. I mean, kind of solve the problem. We know how to make a low area. It's not such a big blow up. But the main challenge is low randomness and low latency, because for now, until now, everybody was like not talking about the randomness. We have randomness, but where this randomness comes from, it was kind of kept silent. But we actually need a lot of randomness often, and we have to think about this as well. So we try now to design actually schemes with as less as possible randomness, if possible, even without randomness. And the other, so far I was only talking about hardware. For software, so far it was believed that it's easier to protect software because people just thought it's easier. But actually, it's not easier because, first of all, we don't have the noise that a hardware implementation has because everything is sequential, while in hardware you have a lot of parallel things, and this makes it a bit more noisy, and you need noise to hide secrets, basically. And when the noise is very low, the security goes down, and this is what's happening in software implementations. But let's start from the randomness first. So I'll present two works that we did work on minimizing the randomness. The first one is tree proposal that where we were using the so-called changing of the guards method. This is a method that Jan Damen some years ago proposed, and he's basically reusing randomness from previous cycles. So he's just putting one in the beginning, fresh randomness, and then reusing it. So we were using this method to actually design AES implementations, with different trade-offs. And then the second paper that I will talk about is a very recent one, which is actually the main two authors are Italians, where they have managed to design the first optimal universal construction for first order TD+1 TIs, projective S boxes. And they managed to do this with T+2 shares. We know that with T+1 it's not always possible, so, but now we have a generic construction, which means that we don't need any randomness because it will be uniform by design. For the first work, I'm just showing the results. As you can see, design 1, 2, and 3 are the ones that we propose, and they have zero randomness, and all the other latency and area are actually quite comparable to the state of the art. And this is how, at the corner, is how we reuse the randomness. Then for the universal uniform masking formula that we proposed. So we have TD+1 TI, where the theoretical lower bound on the number of shares is T+1. But not always. We have examples for 3 and 4-bit permutations when this is not possible. This bound is not achievable. So, and in these cases, when T+1 is not achievable, we observe that we can share with T+2 shares. So we started from this, and then we came up with this beautiful formula for which gives for any function with algebraic degree t a sharing with T+2 shares. And why this is a correct formula? It's actually visible quite easily that it's correct. Okay, believe me, it is correct. The most important, the non-completeness, you can see that the first function, the first component function depends only on x1, so it doesn't depend on all shares. The second and further on, they always depend on all but xj minus 1. So x2 does not depend on x1, x3 does not depend on x2, and so on. And we also have a proof that it is uniform. And because it's uniform, we don't need any additional randomness. Of course, this is not the minimum, always the minimum number of shares. It will probably give a bigger area, but as I said, it's always a trade-off. So the theorem that we proved says that it is sufficient for a function f to have algebraic degree at most t, making the construction viable even if f has algebraic degree strictly lower than t. And then the result is also of separate importance for the research of permutation polynomials, which gives a method for constructing new infinite families of permutations. Okay, so this was about hardware implementations. Let's talk a little bit about software implementations. And this is a paper that has been awarded the best paper award at CHESS this year, also of students of ours. So what we did was, so as I said, it was believed that for software masking should be easier because there is no glitches or only transition leakages and so on. But in the late years, we have seen a lot of micro-architectural attacks on CPUs, and they are very specific and very dependent on the manufacturer. And as you know, Intel and ARM, they don't tell us what exactly they do, so we have no way to even know how the CPU works exactly. And they were quite devastating. So what we did was, so this is this is a CPU architecture, a general CPU architecture. The plan was the following. So we go through all the architectures of scalar codes. Then we figure out which components recombine data, because this is when they leak, and which components can leak. Then once we know where the leakages are, we can adapt the security notions based on these leakages, and then we can create a new secure masking. And the first goal was to find the leakage sources, and we found that we have three main types of leakage sources: the transition leakage, the glitch-related leakage, and the bitwise interaction leakage. So if you look at the arithmetic logic unit, for example, it works all the time and computes all operations that it supports, and at the end, it selects, at this max, it selects the one that is needed at this specific time. And some of those operations can lead to leakages. Of course, you always compute everything. Because they are all computed at the same time, they are subject to leakages. Transition leakage and bitwise interaction leakage. For transition leakage, for example, if you have this masking, x0 is x plus m and x1 is m, then you can actually, because everything is sequential, you will actually end up in canceling this mask, and then you will know not only the Hamming weight but the Hamming distance of x1 and x, which is enough for the attacker. And also for bitwise interaction leakage, the AND and the XOR operation, they only operate on individual bits, but the AND, the add and the shift, they create interactions between the bits within one operand, which again leads to leakages. And this is the last source of leakage, the glitch-related leakage. This is generic design of a register file with 5-bit address signals connected to with a multiplexer tree of depth 5. So when you perform read and write addresses, this is subject to glitches and potential sequenced access to multiple registers. When you have one clock cycle unit, then the signals can stabilize. There is this called neighbor leakage effect, And when the registers are read, a glitch in the address will result in combination of the shares of the same index, and this will cause leakage because there will be some delay, and then they will overlap how they are not supposed to, and then they will cancel out. So what we figured out we need to protect as a consequence of these various leakage sources is that in order to protect against bitwise interaction leakage, we need to put the shares not horizontally aligned, and to protect against transition and glitch-related leakages, we need them not vertically aligned. And to meet these requirements, we have three new definitions, which are very, come also from the theory of TI. We want horizontal non-completeness, and this is the first picture on the right. So each share is in a different row. Then we also need vertical non-completeness, so not all of them are in the same column, but at least one is in a different column. And we need register uniform sharing, which is everyone is in a different column and in a different row. And we prove that if this is met, then the masking is secure. I will give two examples. First for TD+1. With TD+1 shares, it's like the traditional setting for TI. You've seen it before. You have horizontal non-completeness, where we separate the registers in domains. So each register is a different domain, and each share is assigned to a single domain. And then you have also vertical non-completeness, where you store the shares in registers shifted by a unique value depending on which domain they belong to. And I will give also another example with D+1 share, and for the so-called Toffoli gate. This is the definition of Toffoli gate with blue over there. So you compute C0 by multiplying A0 B0 plus A0 B1, and then summing up with C0. So how you do that? You put them all the shares in separate domains, and you also need one extra domain, a temporary domain where some computations will happen. So first you have to multiply A0 B0. Because they are from the same domain, it's safe to just compute them at the same at R6. Then you can sum with C0. They're again from the same domain. Then you have to have A0 and multiplied by B1. Because they are from different domains, we move them to a temporary domain. Then we compute the multiplication in the same domain. Then we put them back. And then we compute the C0 plus A0, no, we move C0 plus A0 B1 again in the temporary domain, and then we add up A0 B1, and then we have everything computed. And you need 10 cycles for that. This is how you do the whole computation. This has been implemented in the lab. By the way, everything that we design, we implement on FPGA and we test in the lab, always. We use leakage testing and we test in the lab. So it has been, this technique has been applied for Present and for Ketchak and has been tested on RISC-V. I hope you know about RISC-V. This is an open source initiative by many companies and association by many companies and universities where everything is open source. So you can really test how an implementation is done, and then everything that is happening opposite to Intel or ARM or the royalty, the non-free from royalties cores. So, and we also tested it on ARM Cortex M4 core. Okay, and I still have some time to talk about combined attacks, because we talked about passive and active, side channel and fault attacks, but of course the adversary always tries the easiest If you don't protect against side channel, it will try side channel. If you protect against side channel, it will try fault. But even if you protect against both, it might try a combined attack, which means, for example, it would prop these shares and fault the D+1 share in a way that if the result is correct, then he guessed correctly. If the result is wrong, then he knows that it's the opposite. So this is a very young area of research. Not many proposals have been done so far, but lately people more and more realize that it's a very important topic to look at. And also we have to note that the protection mechanisms that you use for side channel and fault are somehow contradicting each other, and actually gives, they both give more possibilities for the adversaries, for the opposite adversaries. So for example, when you protect against side channels, you do masking, which is like you have more surface for faulting, you have shares more than without protecting. While when you do faults, the usual protection mechanisms are redundancy, repetition. So you have like two parallel computations so that you can compare if there was a fault. If they are the same, then you can see that there is no fault. If they differ, then you know that there was faulted. And this gives more opportunities for leakages if you consider the side channel adversary. So they are not easily combinable, both protections. So what we did was, again, we went to look at the MPC world because they have already been doing these things. And as we have seen before, we have the passive, the secret sharing, and the masking is like translating secret sharing into the embedded systems, the TIs and everything that we know so far. For active adversary, we have the Spitz protocol. So what do we have for the combination of both? How should we look at this? What we did was we actually had two approaches. You can either start from Spitz protocol and translate it into the physical world, or you can start from the masking that you know, the side channel protection that we already have developed, and add, in a way, protection against faults. And this resulted in two different countermeasures. One is kappa and one is M&M. Kappa is very impractical, very big, but it's provably secure. It's completely based on Spitz protocol. It's a framework. It's just a way to show that we can actually design a protection against combined attack, but you wouldn't use it in a chip because it's too big. Well, M&M is not as provably secure as kappa, but it's very practical, and it's actually very easy to implement. I'll go shortly over both of them. So the main thing that we use in both is we use for the detection mechanism MACTAX, information theoretic MACTAX with the key alpha, where for every data block X there is a tag, which is obtained by doing some Galois field multiplication with the key alpha. Alpha is constant through the entire implementation, but has to be fresh for each encryption. And of course, the probability of a fault attack to be consistent is 2 to the power k times m. Of course, the higher m you choose, the better the probability you have. Again, let's compare with MPC. There are some subtle differences between MPC and embedded security, because in MPC you have very expensive communication, but you have basically unlimited local memory. It's relatively cheap. While on the chip, the communication is for free because it's just wires, but the storage is very limited. So these are differences that we have to take into account when we design the countermeasure. And it asks us to do some changes to adapt. So we have introduced this tile, prop, and fault model, which this picture you have seen already. When you have areas in the chip that you call tiles, and then you allow the adversary to fault or to probe a certain amount of these tiles. So for the side channel adversary, it can probe all intermediates within D tiles out of D+1, and can have correct value disclosed with probability 1. The fault adversary has two options. Either can have exact and known, very precise laser, for example, up to D tiles or, with probability 1, or it can be a random fault, which corresponds to the clock glitching, and it can be on as many tiles as it wants. There's no restriction on that. And the combined adversary is a combination and interaction of faults and props within these D tiles. So for kappa, we just use spits. We use the beaver triples, how it is generated there, with some differences, of course, because we cannot store them. We just do them on the fly and things like that. We don't use, of course, FHE because it's too expensive for putting it on a chip, but we have different techniques. I'm not going to go into details there. For M&M, I'll talk more about M&M because we have a newer paper that that actually reports an attack on M&M, which is out of the model of M&M, but still it's an attack of M&M. It's just using any masked multiplication, TI, DOM, SCM, whatever you want, and then computes the masks and tags using this multiplication. We have a small problem when computing the tag, because when we multiply two tags, we get alpha squared instead of alpha, but then we multiply with alpha inverse, and then we get the correct tag. You can also do other operations like power functions. Also, you have to correct the tag. You also can compute the inversion function. Again, you have to correct the tag, multiply with alpha squared, but this is a linear operation, so that's not a problem. So, if you remember, just before I showed you how we compute, how we implement AES using the tower field approach. And we have a new paper, as I said, for chess next year, actually, in the first edition of chess, where we provide an attack on M&M. Actually, M&M has been implemented on an ASIC, on a chip, and tested in a lab in Japan. And they discovered some problems and discovered an attack on it. But before I start with the attack, I'm just putting here some of the formulas, how we do the multiplication and the inversion. And for us, this lambda function will be very important because we use it later in creating a new countermeasure. So multiplication, this is when you go from GF2 to the n to GF2 to GF2 to the 2n over GF2 to the n. So this is how you do the multiplications and the inversion. And lambda and lambda minus 1 are computed in stages 2, 3, and 4. So what you see here, we start from 8-bit, and then this is split in 2 parts. Then you go to 4 bits. And then if you can see that the top and the bottom lines are just going from the first stage to the last without any operations in between. But in the middle part, you have consecutive operations. So you have 4 different stages. And this will actually make the attack possible. So let's first talk about ineffective faults. What does this mean? So you have X and Y are the inputs, and then you perform a fault attack on one of them, for example, on X. But we have a mechanism to detect faults. So at the end, we will see that the result is Z prime, not Z. So we'll know there has been a fault attack, right? But what if Y is 0? Then 0 multiplied with anything is always 0. So at the end, we will get, the attacker will get 0. And he will know, first of all, so Y was 0 if he got 0 because he faulted X. And second, he will also, the fault will be undetected. We will not know because it's 0. If he faulted or not, this value, it doesn't affect the multiplication. So this is the so-called ineffective fault. And this is what the type of attack that we are actually using. So it's a glitch attack using glitch faults. And it results in a random value in the circuit with the longest critical path computation. So the red lines, they go directly from the beginning till the end, so there is no computations in between. They are not affected because there is no computation, and that's the shortest critical part, but the central part is affected because this is the longest critical part. And the MAC-TAG, because we have MAC-TAGs, will detect such an attack since the must value and the tag will not match anymore. But let's assume we attack somewhere in stage 2 or 3 or 4. And when the input is 0, these red lines, they will go from the beginning till the end without any change. And then they will just nullify the errors that have been done during the computation of these middle stages. So it will actually be not detected, and it will be faulted, and the attacker will know that X was 0. So the attack has been performed on the AS implementation, and these are the results from the simulator. Now we are going to use the homomorphic property of this lambda function that I told you will be important. We have proved that this is a homomorphic function, and we use this homomorphic property to do cross-checks during the computations in the AESS box, in the AIM&M. And how we do that? So now we have this parallel computations of the value and the tag, and then every time in each of the stages we used compute lambda of alpha, and then we put it in the multiplication, and we check for every stage if the tag is correct. So in this way, there is no way that even if x is 0, we'll catch a fault at each moment when it happens. We are not waiting until the end to check the mark tag, but we check every time. So this is more or less what I wanted to say. Just to conclude, I think I'm well on time. So the theory of hardware masking has developed a lot all over the past years, and but still some challenges remain open, mainly on optimizing on some resources, mainly, for example, in randomness and latency. And TN has been playing an important role as the first probably secure masking technique in presence of glitches, and has been used a lot for protecting all kind of, basically any symmetric cipher, and also became a basis for many masking techniques built on top of it. It can also be showed that it can also be adapted for masking in embedded software, because originally it was for hardware. And also I would like to emphasize that combined attacks are very important, and that in the last years there have been quite some proposals for different types of combined attacks, but there is a lot of work to be done there as well. Thank you very much.
Thank you very much for this excellent talk. Sorry, my voice. Any question or comment? No question. Right. Okay, thanks again. Thank you.
think that.
But they have to put it. Okay.
No, this is the next one.
Second one is about boomerang attacks, which can be viewed as a generalization of differential attacks. So the first talk is given by Marco Calderini from University of Trento, Italy, and it is a joint work with his co-authors. So please, Marco, it's up to you.
Thank you.
You can start.
Good afternoon, everyone. So today I will talk about differential attacks, but trying to use a different operation with respect to the classical one, which is the XOR. And I don't know. Okay, didn't push the. So differential attack effect in particular block cipher, and we can think about the block cipher just a set of permutations or encryption function, and we can individuate each of these functions using a certain key. And we select a key, we have our encryption function, then we can encrypt a given message, which is just an element of a vector space over the binary fields. And what we want usually, we want that the algorithm that permits to compute the encryption of a given message is an efficient algorithm. And for this, there are several different kind of design. One of the most used nowadays, in particular EAS, is designed with the substitution permutation network structure. And in this design, we usually divide the encryption function. We just iterate several operations in order to obtain at the end our ciphertext. This operation can be defined like we have the S-box part, which is called also the confusion layer. And at this level, we just split the message in smaller blocks. We try to put some nonlinear operation here, trying to lose some of statistical properties. And then we just combine all the blocks. We apply a diffusion layer, which is just a map that tries to diffuse this confusion to all the bits, and then we have at the end the key addition layer, where we put our secret key inside our message. And then we iterate this process for some number of rounds. And in particular, if we can think, usually we divide our message in blocks that are usually 4 or 80 bits, and this is just for some hardware constraint, usually, more efficient to implement this kind of string bit. So, and then we apply a permutation to each of these blocks, which is this the map gamma, and then we apply a linear permutation lambda to diffuse all this confusion introduced from the gamma map. And then we add usually the operation that we use, but it's not the only one, but usually we XOR the round key. So the operation for adding the key is the XOR operation. So how does it work, differential cryptanalysis? Well, differential cryptanalysis was introduced by B.M. Shamir in 1991, and the idea is like to try to analyze how the input difference affect the output difference of the ciphertext. So we put in input two different messages with a given fixed input difference, delta, and we look at the probability of obtaining an output difference, delta y, at the end of the encryption. Due to the design of a substitution permutation network, this analysis can be reduced to analyze each single round function. So we just need to understand how this difference propagates along all the smaller blocks, let's say. We can immediately see that since this relation, this difference is just a linear operation between the two plain text, so of course from the linear diffusion layer and from the key addition layer we don't have any problem because the difference just propagates in a deterministic way. So we know for sure that from the lambda map we just need to follow the image of the difference through this map, and from the key addition layer we know that if we enter with a given difference delta, the output difference is the same. What it change is the S-box layer. At the level of S-box layer we need to analyze all possible equations of this form, like gamma x plus gamma of x plus a, and we look what is the difference of these two. And usually we try to individuate equation that admits more solution as possible. And this maximum number is called the differential uniformity of the S-box. And the attacks highly depend on this property of the S-box. So the classical solution in order to avoid this kind of attacks is like try to use an S-box that has a low differential uniformity, as low as possible, and a linear layer, the linear map, that has a good diffusion property. It means that we want that at the end we want to involve as S-box as possible, as much as possible, in order that the probability of this attack drops quickly. But all these measures that have been introduced in order to avoid this kind of attack actually are based on the XOR operation. So the nonlinearity properties of the S-box in particular are based on the XOR operation. That means if we look at the group theory, so to permutation group, we are focusing on the translation group induced by the XOR operation, so which is T plus, but this group is just an elementary abelian regular group. But what if we consider a different group with the same property, which is just an isomorphic group to the translation one? So we can consider any abelian regular group elementary, and we can individuate the map inside this group in this way, like the map tau k is just the only one maps that send 0 into k, and then we can define the operation, the alternative operation circle in this way. And we have at the end, it's easy to show that the resulting space V with this new operation is just a vector space over F2. So the question now is, can be that we have a block cipher which seems secure with respect to the classical differential cryptanalysis, but not for a new operation. And in order to understand if this kind of operation can affect this kind of cryptanalysis, we need to start to select what are suitable operations that we can actually use in an attack. Well, the first thing is we need to count a lot of sum with this new operation. So we want to do this operation in a quick way. And the first thing is, okay, just focus on affine maps. Affine maps are very easy to implement, very easy to compute the output. It's very fast. So we target a subgroup of the affine group, the classical one. So then, for the S-box level, we just need to focus on map. We need to find an operation that permit to have a differential uniformity with respect to this new operation, which is higher than the classical one. This is easy to analyze usually. We can do this just computing the so-called differential distribution table. Then we have the linear layer. The linear layer is linear with respect to XOR, but what about this new operation? This is the big issue in this kind of analysis. Because if it's not linear, these maps, it's impossible to determine the distribution of the difference of this map, because it operates on a very large number of bits. Then the key addition layer. Well, in the key addition layer, we can note these things. So this equation, we have that the translation through the element k of x circle the translation applied to x circle delta. Well, if we force to have this translation inside the affine group, but with respect to the new operation, actually this equation does not depend on the input x. So just only on the key. We don't know the key, this is another matter, but at least we lose the dependence on x. So we require also that the translation group T plus is inside the affine group with respect to the new operation. So we want to use this kind of groups that have these two properties. These groups actually have been characterized in a work with Roberto and Massimiliano Sala. And we saw that for studying this kind of group, there is some particular space that we can associate to a given operation. And the one, W, is the set of all elements for which the translation with respect to the new operation is actually the classical one. So it's just an element for which this translation is in the intersection of these two groups. And then we have also another subspace U, which is given by the space generated by the product of the element A and B, with the product defined in this way, with the XOR of A and B, and the XOR with A circle B. One of the, we have a constraint on the dimension of W, and at most we can have a dimension of equal to n minus 2. A first differential cryptanalysis based on this kind of operation have been introduced actually by Roberto, Civino, Blundo, and Sala, and in 2019, and they provide the first example, a toy cipher, for which it was possible to show that the classical differential cryptanalysis actually doesn't give any information after 5 rounds of this cipher, but with respect an operation which was actually on the last S boxes, it was just the XOR, but on the first S boxes, it was actually an operation based on this translation group. And with this particular property of the dimension of W equal to n minus 2, so they were able to mount a distinguished attack on 5 rounds. But our idea, so what I want to give an idea of what is inside this analysis. We need to analyze the key addition layer, and if we have that our maps, our translation are actually affine with respect to the new operation. The output from between these two elements is just the difference delta plus some error, which is a product between delta and k, so it depends on k, but when we focus on operation for which the dimension of w is n minus 2, the dimension of u is 1, so we can have only 0 or another element different from 0. So the difference, as with probability, propagate is a delta with probability 1/2, and otherwise could be delta plus u with probability 1/2. It's just split in those two possible output. So this part is quite solved. Okay, but what about the linear layer? Well, the optimal solution would be if also for this operation the linear layer is still linear. So is in this intersection between these two groups. And Civino, Blondo, and Sala characterized for the case where the space W has dimension n minus 2, they were able to give a characterization of all maps inside this intersection. And for doing this, we just assume the structure of W generated by the last element of a canonical base. We can always assume that, and so on. And we have this nice representation. Well, in this work, we decided to study the problem. What about if we consider not the XOR in the last part and only in the first S box a different operation, but a different operation for all S boxes, so in all blocks? Because actually the mixing layer used, the diffusion layer used by Civino, Blondo, and Sala, the diffusion property was not too slow, but we can find a diffusion layer with better diffusion property. So can we obtain some diffusion layer that in this intersection, in these two groups, actually looks much better than the one, but we still gain something from the difference operation? So the first step is, as in the work of Civino, Blondo, and Sala, is try to understand which kind of map we can have in this intersection. So we consider this setting where in each block we are acting with a difference operation, but the dimension of the space associated with this single operation is always the dimension s minus 2, and in this way we can, up to conjugation, stay in the similar setting as in the result of Civino, Blondo, and Sala. We can assume that the operations are the same for all blocks, and this permits a starting point for the characterization of this subgroup. So, starting from the characterization of Civino, Blondo, and Sala, we just divide in blocks our matrix, and then we obtain this huge, ugly theorem. It's a lot of points, but it says that actually we can have only one block A, which is on each row and each column different from 0 and must be invertible in that case. The blocks B can be anything, so you can play as you want with this part. The C blocks are 0, and the D blocks satisfy this property. Like if A is 0, the corresponding A is 0, then B is in the kernel of D, B is associated to the operation, then otherwise it stabilizes the vector B, and the whole matrix with all the blocks is invertible. So then we move to analyze the S-boxes part. Well, at this point we focus on 4-bit S-boxes, the invertible ones. These S-boxes have been classified up to affine equivalence, which I gave here the definition, by Leander and Postman. And in total we have 302 classes up to affine equivalence, and 6 of them are so-called optimal. They have optimal cryptographic property. So among these properties that for the optimal function, we have that they are 4 differential uniform, which is the best one for bit permutations. And what about and this is just the representative of these 16 optimal S boxes. But what about the differential uniformity with respect to different operation? Well, it's not inside the same affine class. Now we can have a different element that doesn't have the same differential uniformity. So we need to analyze any function inside this, any affine class, which is quite difficult, but we can reduce actually the analysis to consider componing this our representative GI with 2 elements of that we can take among the coset of the space H circle. And doing this, we were able to perform the compute the differential uniformity of these maps in the classes of this optimal representative. And as you can see, there are sums for which we can obtain inside an affine class of some of these some function which has actually differential uniformity 16, which is the worst case here. So maybe just selecting one of these, we can implement this kind of attack. We did some experiment. We consider this mixing layer was constructed using the characterization, and just put here, it's not interesting. The selected operation on a single block is represented by this table. I put in red where we have the difference with the XOR operation, where in the black one, the XOR operation actually coincide with this operation. And then we select our S box. The S box that we selected is this one, is equivalent to G0, so is an optimal one, and you can think that is a affine equivalent to the S box S1 of the cipher serpent particular. And you can see that the differential distribution table with respect to the XOR, we have at most, apart the 0-0 difference, which is deterministic, of course, at most the differential uniformity is 4, but with the new operation, the selected operation, we reach 16. Then we just take the substitution permutation network with this diffusion and S boxes. We perform some analysis with round keys, which have been taken random, and we analyze which are the best difference with respect to the XOR and the best difference that we obtain with respect to the new operation. And at each step we were able, at each round we were able always to obtain a higher probability that our diffusion, our difference propagate among all the rounds. So this provide, with this we can see that actually if we target this kind of cipher for which we are able to construct the diffusion layer, which is in this particular space H, then the differential gate analysis with respect to this new operation is more effective than the classical one. Then I put some open problem that we want to try to study, like which are the round keys that permits a better implementation of the attack. Like can we individuate some weak keys that permit to diffuse much faster our, much slower our difference. And maybe this could be like an idea for constructing a case schedule algorithm backdoored. So it's not the good guy. And then what about if we change, not we don't focus just on the case n-2, where the dimension of W is n-2, but what about the case n-3? We were able also in this case to characterize the the subgroup H, but only when we are considering on the whole block this kind of sum, not in parallel way. This is still open. And thank you.
Thank you so much, Marco, for this very interesting and promising operation for in the context of the differential attacks. Any question from the audience or comment? Okay, thanks again.
Thanks.
So we wait 6 minutes. We start at 4 now. What? Now you continue. Okay, Ali. So the next speaker is Loïc Rouquette from France, from Lyon, University of Lyon. It's a joint work with Marine Minier and from Nancy University, and Christine Malmon. And it's about, yes, boomerang attacks and related topics, Xboxes and so on. Please, Loïc.
Thank you for the introduction. So today I will speak about differential attacks on the Rheindal, which is the non-standard version of AES. So in the first part I will do a recall of the differential attacks and the boomerang attacks. And after I will speak about the design of Rheindal and the implementation of the search of differential attacks on the cipher. So to begin, differential attacks were designed by Biam and Shamir in 1991. The idea is to analyze for a symmetric cipher the probability to observe a given output difference when we inject an input difference in the cipher process. So to do this, it's very simple. We select a plaintext P1. We can cipher this plaintext using a cipher scheme. And we obtain a ciphertext from this plaintext. After that, we can use a second plaintext P2, which is not a random plaintext, but a bit plaintext that is created by injecting an input difference using the bitwise XOR operator from P1. So we have a strong relation between P1 and P2. When we have selected P2, we can cipher P2 and obtain a second cipher text, which is a C2. And we can compute the differences between the two ciphertexts. So the idea of the differential attacks is to analyze the probability of having this output difference when we know the input difference of between the two plaintexts. So if the probability is high enough, we can extract information from the cipher. So the boomerang attack was a variation of the differential attacks. This time we do not only inject a difference between the two plaintexts, but we will create a translation for the ciphertext to obtain a new ciphertext. So in this case, we choose two plaintexts P1 and P2, the same way as for differential attacks, by injecting an input difference alpha. We cipher them to retrieve the two ciphertexts C1 and C2, and after that we inject another difference, which is delta. And we obtain two shifted output ciphertexts, which are C3 and C4. And we decipher this new ciphertext, and we retrieve P3 and P4, and we check if the input difference that we obtain after deciphering the two new ciphertexts are the same as the firstly injected difference. So to compute this, we can model the cipher as a composition of two subfunctions. And we do not fix only alpha and delta, but we can also fix intermediate differences that are beta and lambda elsewhere in the part of the cipher when we want to decompose the cipher. So the problem is that with this representation, we know the differential, and sometimes the probability of the differential match may be worse. So to counter this drawback, BM introduced in 2001 a new attack which is called sandwich attack. So in this sandwich attack, we separate the cipher in three parts. So we have E0, EM, and E1. E0 is a traditional differential distinguisher. E1 is a traditional differential distinguisher. And EM is the part that is that must manage the differential probability from beta to lambda. And as it is a very slow differential trail, we can compute the probability more easily than computing the probability of the whole boomerang. So to compute the probability of the sandwich attack, it's quite simple. You compute the probability of the upper distinguisher, which is the probability to obtain alpha and beta. After you compute the probability to go from beta to use lambda and to go back to beta. And for the lower part, you compute the probability to have a differential lambda that goes to the differential delta. The overall probability of the boomerang distinguisher can be computed at the square of the lower and the lower differential probability times the probability that is used in the middle part of the boomerang attack. Once again, we have a problem here, is that the attacker needs to specify how to cut the cipher in order to select the size of E0, EM, and E1. And in order to counter this drawback, Dolan and co-author introduced in 2010 a new model that manage the cut of that automatically manage the cut of the three different layers of the attack. So here I will explain in detail the model of Dolan and co-author to construct the boomerang distinguisher. So in the middle part of the distinguisher for the EM layer, we need to represent the S boxes, so the nonlinear operation in the ciphers, in both encryption and decryption direction. And we need to represent the four differences of our distinguisher. So we have alpha and beta, which appears in the lower part, so in the encryption direction, and lambda and delta, which appears in the lower part of the boomerang, so in the decryption direction. So to model this, Dolan and co-author introduce three variables. So they are big delta upper or delta upper, which represent the value of the difference for the big delta, which represents if the S box is active or not in the upper and in the upper part, and the 3x and the 3sb, which represent if we need to know the value of the alpha and beta values. You will see later that in some cases you can compute the probability without having all the information of the square here. So we have three variables that indicate if one S box is active for the upper part, and we have the same variables which indicate if the S box is active for the lower part. So now we will see that to compute the probability of the distinguisher, we need to compute the probability of the S-box in a different configuration. The usual configuration for the differential attacks is to compute the probability of only one trail, either in the upper or in the lower trail. And if in this case, we can compute directly the probability to go from alpha to beta. And in this case, you can see that for the upper part, we activate the S-box. And for the lower part, we do not activate the S-box. And we have the lower part do not appear in the representation. The same thing if we want to activate one non-transitional non-linear transition in the lower part, we can activate only the lower part of the S-box and deactivate the upper part. We can have these things that can be activated in both trails. So in this case, for example, you can have a difference which is propagated in the encryption direction and which is also active in the decryption direction for the lower part, for the upper part. And this is the representation for the encryption and decryption activation for the lower part. So this is the main transitions that are used for E1 and E0. But it is automatically selected by our model. In the middle part, we have the boomerang connectivity table. So this is the probability to go from alpha to use delta and to go back from alpha. And we see that in this case, we can compute the probability of the square without fixing the value of beta and lambda. And we have several other transitions, which are lower boomerang connectivity table, upper boomerang connectivity table, and the extended boomerang connectivity table, which define which kind of transition is used in the model. So now I will just introduce the Rindal cipher. So Rindal is the non-standard version of AES. So the main difference between the two solvers is that he has more variants. So he has 5 block size variant and 5 key size variant. The cipher is quite simple. So for a plain text and a key, we have a first operation between the key and the plain text, which is bitwise XOR. After that, we have a round function. This round function is composed of S-box layer, so this is the nonlinear part. After the S-box layer, we have a shift row, which aims to shift the columns of the state. After the shift row, we have a mixed column, which is a Galois multiplication between the column Y and a constant matrix. After that, we XOR, so we add the round key RKY to the state Z to go back to XY, and we repeat this round function a given number of times. After performing all the round function, we enter to the last round, which performs the S-box layer, the shift row, and adds the last round key. So when we have performed all of this operation, we have the ciphertext. Now I will speak about computing the boomerang distinguisher and exactly how to do this on Rindal. So in the case of the model of Dollon and co-authors, we have 2 steps because we cannot compute easily the boomerang distinguisher directly. So in the first step, we want to try to identify which S-box is activated in our trace. So to do this, we use the value x, 3x, 3sb for the upper and the lower trail, and we try to identify which S-box is active. So we add information and constraints to set the rules that correspond to the S-box differential propagation and to the linear layer. This step 1 also determines which transition is used for the second step that will be presented later. And this first step finds an approximation of the probability of the distinguisher. This first step is solved by using the Picard solver, which is a SAT solver. We choose the SAT solver because in this first step, a lot of variables are Boolean variables, and SAT solver are really dedicated to solve this kind of problem. In the second step, we have the two trails that indicate which S-box must be used to be good. And the aim of the second step is to compute the real probability of the distinguisher, but we do not compute the differential distinguisher, but we compute the differential characteristic probability. So the difference between differential characteristic and simple distinguisher is that when we want to compute the distinguisher, we only fix the input difference and the output difference without specifying the path that is used in the cipher in order to achieve this difference. Generally, we compute differential characteristic probability because it's much simpler, and in this case we specify which is the path that is used in the cipher to reach our probability. So the second step is solved in Choco. Choco is a constraint programming solver, and we choose this solver because the representation of the differential distribution table is not well handled by the SAT solver or MILP solvers. So the way we resolve this problem have some drawbacks. For example, when we iterate over the first step solution, we need to be sure that we do not iterate multiple times the same solution. Instead, we lose a lot of time. And the naive way to say that two solutions are different in the first step is to say, okay, if one of the two solutions have one variable which is different, we say that the two solutions are different. But in fact, as in the second step, we only use the S-box transition to fixed values, we can improve our filtering equivalence of the model by forbidding the solutions that use the same trails. So we add the rules that the model considers that two solutions are different if we are using at least one S-box transition which is different. So maybe you can have two models that have one Boolean variables which is different, but if they are using exactly the same path, you will consider that they are the same solution. Still, this improvement will generate a lot of step one solution because you can activate very many paths in the step one solution. So in order to counter this, we make a limit, and when the step one have iterated over a certain number of step one solution, we try the next level of step one solution in order to stop the research sooner. Now I will speak about computing attacks from a distinguisher. In the model of Delon and co-authors, the overall workflow to compute the attack complexity is done in 2 steps, and maybe 3 if we want to have a more precise result. In the first step, we compute the best differential characteristic, which is an approximation of the probability. And in the second step, for this truncated differential characteristic, we want to compute the probability of the best differential characteristic. After this, we can either performing a clustering analysis in order to improve the probability of our distinguisher, or directly try to compute the attack complexity by performing handmade key recovery on the model in order to compute the attack complexity. So, how to compute the attack complexity from a distinguisher? In our case, we use the attack of Zhao and co-authors, and we see that you can have this kind of formula, which is the attack complexity. And on the right, you have the scheme of the attack. So we have an upper part and a lower part, which is the number of rounds we need to add before the distinguisher and after the distinguisher in order to complete the attack. And in the middle part, from E0 to E1, we have the distinguisher part. So for example, in this case, to compute the attack complexity, we need to have several values. N is the block size, so it is given by the specification of the cipher. We have NB, NG, and NF, which are the size of the number of rounds which is added before the distinguisher, the number of rounds of the distinguisher, and the number of rounds which are added after the distinguisher. We also have a P Q square R, which is the probability of the boomerang distinguisher in the middle part. And after that, we have some other values like MB, which is a number of bits which is activated in the key schedule at the beginning of the cipher process. And RF, which is a number of ciphertext bits which is active in the ciphertext at the end of the attack. So we change the optimization process in order to integrate this kind of improvement directly in the model. So instead of computing the distinguisher in a first part and performing a key recovery handmade in the second part, we directly try to improve the attack complexity in our model and directly get the attack complexity at the end. We do not add this, but we can also add an optional clustering analysis improvement in our model in order to increase the quality of our complexity. So in results, the first result we have is the computation time for the different instances. So our model is quite time consuming. As you can see, the more you add the round, more you use time, and the main issue is the first step. So in the first step, we spend a lot of time, and if we need to improve the overall optimization process, it may be the point to do. So we find a new 9-1 attack on one version of Frindal. So it's required key encryption that is lower than exhaustive search. We have a success probability of 97%. And this is a weak key attack, so it does not work on all the key because it's a related key attack, but the number of key is quite large. So to conclude, we building an efficient model for a boomerang search is quite hard. And we find that sometimes valid boomerang distinguisher may not lead to valid attacks because we activate too much plain text or too much ciphertext, and the overall formula complexity will be higher than the exhaustive search complexity. In further work, we want to integrate this kind of modeling into Tagada, which is a CP-based library, in order to fully automatically generate the moment distinguisher from the cipher specification. And we want to improve the simplification of our model in order to reduce the computation time. Thank you.
Thank you so much for this very nice talk. Any question, please, from the audience? Okay, I have a question.
Yeah.
You know the story about the variation of boomerang, C boomerang, etc. So you know this or not? Where this kind of I mean, in each the equations. I mean the BCT, etc. Is variation of C BCT, in which C is in not in one. Don't take the value one, but different value from the finite fields. You know this?
No, I do not know.
Okay, bon,
I do not know.
The question is, okay, no problem. Okay, thank you so much for this, for all our speakers, and I wish you all the best for the continuation. Now it's a coffee break, and
Wait, see.
Okay.
Yeah, okay. Before we go to the coffee break, which isn't ready, so don't panic. So I want to say three things. So first of all the talks you have heard in this day in the main session, they'll be published on a special issue of Journal Mathematical Cryptology in January, which will be open access, so everybody can read. So if you like any of them, please download and cite our paper, so we'll get more funding, organize more events. So that's matter number one. And also, most people here are members of the association. People who are not, if you are Italians, please become member. And also, if you're not Italian, but if you are an EU citizen, if you are from France, from Germany, from Bulgaria, you can join, become a member. So consider that. And finally, I wanted to thank the people that did the hard work of reviewing. So we selected paper, we had the program committee, and they did very good work and selected good papers. And one of the two program chairs is Professor C.M. Messager, who was now chairing, and she also recently got the International Boole Prize. She's a world expert in Boolean functions, so thank all of them. Okay, now we can go to coffee. Please come back to the main hall. To start. Okay, now is the last session devoted to cloud encryption. This will be chaired by Professor Giulietti of the University of Perugia. I already introduced him, but anyway, for people who come only today, he's one of the founding members of the association. He was the first vice president of the CIFRIS. Massimo.
Thank you Massimiliano. Welcome to this last session. The first speaker is Irene Villa from University of Genova, and she will talk about searchable encryption, joint work with Marco Calderini, Riccardo Longo, and Massimiliano Sala.
Yeah, thank you very much for the introduction. So I guess, no. Qual è questo? Ah, okay. Yeah, so I'm gonna present a searchable encryption scheme that together we made together with the with Marco Calderini, Riccardo Longo, and Massimiliano Sala. Let's start with some introduction. So, cloud platforms are useful technology that help us to perform many things, such as safely store data, share data, and also we use it to sometimes to delegate expensive computation or delegate the cloud to perform some searches over data. But in this world, we know that we cannot trust anyone, especially some like external platforms. So we do not trust the cloud server, and this means that we want sensitive data, but in general, every data that we own to be stored encrypted over this platform. And for to solve some of the problems that arise from like storing encrypted data, there were implemented many primitive cryptographies that try to achieve secure and efficient usage of the cloud, such as homomorphic encryption, functional encryption, and other cryptographic primitives. Among them, we have the searchable encryption. That the idea is that with searchable encryption, we can allow the remote server to perform some searches over our encrypted data on behalf of the client, but this without letting the cloud to know about what's the plain text, what the value of this encrypted data. So what's the idea or how is this is achieved? So we have our documents. From our documents, we extract some like keywords that characterize the document. And then using a searchable encryption scheme, we encrypt this keyword, so we produce some searchable ciphertext. Then we associate this searchable ciphertext with the encryption of our document. And then we store this in the cloud. And then if we want to perform a search, so we want to look for documents that are characterized by a keyword, then we take this keyword that we want to search, we generate a trapdoor, and we send this trapdoor to the server. And then the server, given the trapdoor and given all the searchable ciphertext that he has stored, he performs an algorithm called test, which is actually test whether this keyword is contained in the searchable ciphertext. And when he gets a positive answer, then he knows that this is a document that we are interested in, so he will just send us the encrypted document. The first searchable encryption scheme presented or in literature was with symmetric setting. And then later on, in 2004, Bonnet and his collaborator proposed the first searchable scheme instead in public key setting called the public key encryption with keyword search. And basically, a searchable encryption scheme in these public settings, it consists of these different 5 algorithms. So we have the classical setup, we take in input a security parameter, and we have in output some parameters. Then the key generation algorithm that takes in input the parameters and provides the pair of keys, the secret and the public key. To encrypt a keyword, we use an input the public key and the keyword, and we produce a ciphertext. And then we need to also produce, to be able to produce a trapdoor, so we take in input the secret key and the keyword, and we produce a trapdoor. And then finally, the test algorithm that takes in input the public key, a ciphertext, a trapdoor, and then it outputs true if the keyword contained in the trapdoor coincides with the keyword contained in the ciphertext, and false otherwise. So using this setting, any user can produce a valid ciphertext, because to encrypt, we only use the public key. But then the problem of using this type of algorithm is that these are vulnerable of offline keyword guessing attacks, in the sense that in real world, the amount of keywords are words, and the amount of possible keyword is rather limited. So an attacker could just encrypt all possible keywords, so produce all these ciphertext, and then test whether the trapdoor that some client sent to the server coincide with one of these ciphertexts that he produced, and then he will recover the value of the keyword that the client is looking for. So he will able to guess correctly guess the keyword that the client is interested in. So to address this issue, it was added another layer of authentication. So with this publicly authenticated encryption with keyword search, in which basically the idea is the same as the one we saw before, but then there is another, so we have 2 pairs of private and public key. One for the receiver, that is the one, so let's say one for the sender, that is the one sending the document in the cloud platform. So we have an algorithm that produces the pair of keyword for the sender, and then also an algorithm that produces the pair of keywords for the receiver, that is the one performing that wants to perform the search. And then the encryption that is performed by the sender will use the public key of the receiver, the secret key of the sender, and the keyword, and will produce a ciphertext. And on the opposite side, the trapdoor will take the public key of the sender, the secret key of the receiver, and produce the keyword, and produce a trapdoor. And then to test a trapdoor and a ciphertext, we have to take also the 2 public keys, and then this algorithm will tell us whether this underlying keyword coincides or not. So using this setting, we solve the problem of this keyword guessing attack. And when we talk about this scheme and the security of the scheme, we use this notion. So from one side, we want the ciphered keyword indistinguishability, in the sense that we want that the attacker is not able to distinguish which keyword is associated to a ciphertext. And on the other side, we want the trapdoor indistinguishability, in the sense that we don't want the attacker to be able to distinguish which keyword is associated to a trapdoor. And okay, so this was the introduction. Now I'll present our proposal for this searchable encryption scheme with authentication. Our scheme uses pairing, so we'll just recall here what's an admissible bilinear pairing for 2 multiplicative groups of order prime p. So we have a map that takes a pair of elements in G and outputs an element in this other second group GT. And we want this map to be bilinear, non-degenerate, and that is efficiently computable. Okay, so let's start presenting the algorithm actually composing our scheme, our proposal. So we have the setup that takes an input as security parameter lambda and construct these 2 multiplicative groups of prime order, G and GT. We have G, a random generator of G, an admissible bilinear map E, and then we have 2 hash functions. The first one that takes an input sequence of bit of any length and give us in output an element of G, and the second hash function that takes an input in G and give us in output an element of ZP star. And all these elements that I mentioned compose the set of parameters. Then the algorithm to generate the key, just too shortly, we just put in the same description because it's basically we are doing the same thing. So given a parameter, we just randomly select an element in ZP star, and then the pair of public and secret key are just this random element and G to this random element. So for the sender, we have A and G to the A, and then for the receiver, we have B and G to the B. And on a note, so possessing their own private key and sharing the public key, now the sender and the receiver, they can construct some common secrets. In particular, they can construct 3 common secrets here that we displayed here. And these are H, T, and S, where H, T are elements of the group G, and S instead is an element in ZP star. And H is G to the A times B that can compute it knowing the private key of one of this sender receiver and the public key of the other guy. And then knowing H, sender and receiver can just compute the hash with the second hash H2 of H, take G to this value, and they obtain T. And then knowing T, they just again compute the second hash H2 of T, and then they obtain S. So this means that given this user, given his pair of public and secret key, knows these 3 secrets, and we will just assume that these are known, and we don't need to compute them anymore, or will not display how to compute them in the slides. Okay, so how should we encrypt a keyword? So we give W a keyword, so it's a word, so it's sequence of bits of fixed length, of arbitrary length, sorry. So the encryptor is the guy that wants to encrypt a keyword is the sender, so he owns the public key of the receiver and the secret key of the sender, so he knows the 3 common secrets, H, T, and S. And then the sender randomly selects another element R, and then he computes ciphertext that is made of these 2 different parts, C1 and C2. So in C1, it takes the secret key and it multiplied with the hash of the public key of the sender and the public key of the receiver and the keyword and all this hash value to the power of s, and then multiplies with g to the r, and then the second block of the ciphertext is just simply h to the r. So from the title of our presentation, it was searchable encryption with randomized ciphertext and keyword, and you can see now why we say that we have a randomized ciphertext, because of this R value that makes our ciphertext randomized. And then instead to create a trapdoor, again, we give a keyword W, the public key of the sender, the secret key of the receiver, so the 3 common secrets. And then in this case, the receiver that wants to perform this search will select randomly element raw, and outputs now a trapdoor that is made of 3 different blocks. So the first block is the pairing of t time of stimulus before we compute this hash value to the power of s with h to the power of rho. The second block is simply g to the power of rho, and the third block is simply h to the power of rho. Okay, and again, you can see that this value rho is in all of these 3 blocks, so that's why we get, again, a randomized ciphertext. And then to test whether the same keyword is contained in a trapdoor and in ciphertext, we just simply test whether the pairing of C1 with Q3, where with Ci, I mean the ith block of the ciphertext, and with Qi, the ith block of the trapdoor. So this pairing is equal to Q1 times the pairing of C2 with the Q2. Just to be complete, let's just check that actually we wrote something that is correct. So this is the ciphertext. This is a trapdoor. So the trapdoor for keyword W prime, the ciphertext for keyword W, and the test is actually testing whether these things, this formula that I wrote in this block, in this box, it's correct or not. So if we plug in all these blocks C1, C2, Q1, Q2, Q3 in this formula, to the right-hand side and the left-hand side of this formula, we obtain this. And you can see that if the hash function that we choose is collision, so it doesn't have collision, it's collision-free, then the right-hand side and the left-hand side of this formula are equal only if the 2 keywords W and W prime coincide. Okay, so this is correct. And let's talk about the security of this scheme. So let's first analyze the trapdoor indistinguishability, in which we said that we want the attacker not to be able to distinguish which keyword is associated to a trapdoor. And to prove this, or to analyze this, there is a TI, a trapdoor indistinguishability game, in which the attacker chooses 2 keywords, W0 and W1. These are the keywords for the challenge. And then there is another actor in this, the challenger, that randomly selects a bit, beta, and returns to the attacker the trapdoor for the keyword W beta. And then the goal of the attacker is to correctly guess the value of beta. And in the meantime, even before and after the challenge phase was performed, the attacker may ask for valid trapdoor or valid ciphertext. So let's see in more details. So again, with A, we call the adversary, the attacker, and we see the challenger. The game is divided into phase. The initialization phase, just we run the challenger runs the setup, given an input a security parameter, and produce the pair of public and secret key for both the sender and the receiver, and give the public key to the challenger. Then in phase 1, the attacker may adaptively ask for some information, so you can issue queries to for both some trapdoors and for some ciphertext. So there is a trapdoor oracle that, given trapdoor that the attacker selects, this oracle will reply with the correct trapdoor to it, and the ciphertext oracle instead will reply with the correct ciphertext for the trapdoor. Then in the challenge phase, as we displayed before, the attacker chooses two keywords, but then we have a restriction that these keywords were not queried previously in phase 1 to the ciphertext oracle. And then the challenger selects randomly this bit beta, computes the trapdoor for the keyword W beta star, and returns this value to the adversary. Then again, the adversary can adaptively issue queries to the trapdoor oracle and the ciphertext oracle, but the restriction that on the challenge keyword must be still satisfied. And then when he's satisfied with this second phase, there is the guess phase in which the attacker tried to guess the value of this bit beta. And so he produces a bit beta prime, and it wins the game if these two values coincide. And we call the advantage of the adversary the probability that the adversary wins the games minus 1/2, because this the probability they just toss a coin and randomly correctly reply to the challenge. So this is the advantage. So the probability that the fact that it wins is close or not to the probability of just randomly guess. Just to finish the formalities, so we just recall what is a negligible function, in which basically we take a function f, and if for any integer d there exists another integer n d, such that the absolute value of f evaluated in k is smaller, is limited by 1 over k to the d for every value k that is bigger or equal to this value nt. So we say that a scheme is full TI security if the advantage of the game that we just described in the previous slide is negligible in the parameter, in the security parameter. If we add another restriction of the possible queries that the attacker can ask, so we add the restriction that also the challenge keywords W0 star and W1 star cannot be queried to the trapdoor oracle. Then we call about standard security or standard TI security. Instead, we speak about multi-user setting when in the game we just described there are not only one receiver and one sender, but in the phase 1 and phase 2 we can also consider other receivers and other senders. And I'm not going to display the proof, but we were able to prove that under the DBDH assumption, our scheme is multi-user fully TI secure in the random oracle model, where with DBDH assumption, we mean that the probability of solving the DBDH problem is negligible, where the DBDH is the decisional bilinear Diffie-Hellman problem. That basically, again, given two groups and a pairing over these two groups, given three elements, g to the x, g to the y, and g to the z, the attacker is able or wants to distinguish an element of the form E to the pairing evaluated in GG to the XYZ from a random element. Again, and now everything I just talk about for the trapdoor indistinguishability can be just simply transformed in the ciphertext indistinguishability, in which basically we just change the name of trapdoor with the ciphertext. So the attacker select two keywords, and the challenger will produce one ciphertext, and the goal of the attacker is to distinguish which was the keyword for the given ciphertext. So again, the game is basically the same, just we swap the role of the ciphertext and of the trapdoor. And for the cipher indistinguishability, we were able to prove that under the modified decisional linear assumption, our scheme is ciphertext indistinguishability secure, so just the standard security notion in the random oracle model. And here, the modified decisional linear problem instead is just for a group G. We take 4 elements, this G to the X until G to the K over Y, and then the attacker tries to distinguish an element of the form G to the J plus K from a random element. So to conclude, just some comments on, okay, we just talked about to create a ciphertext, to create a trapdoor for single keywords, but what about multiple keywords? Because usually when we have a document, we specify, we don't have only one single keyword, but we have multiple keywords, so there are possible solutions. So one solution is just to encrypt keywords one by one. But this means that in this case, the server may get some partial information because it will know, okay, you asked me to find a document that satisfies these 2 keywords, and I know that this document, I don't know which document is this one, but it satisfies just one, and this other just satisfies another one, so it can get some partial information. Another possibility is just to create a ad hoc ciphertext for the combination of keywords, like is displayed in the second items. But this means that of course, we need to, for every document, we will increase the number of associated ciphertext keyword to it. Another possible solution is, okay, let's say that the sender and receiver, they agree on some ordering on keywords. And so the ad hoc ciphertext for keywords, and the same is work for trapdoors, is as is displayed in this third item. But then, in this case, it means that the sender has to perform some extra computation because he has to perform more hash values than in the previous 2 points. Just a final note, I think is, that we actually, the role of this value T that we added here in the first, especially in this first part of the ciphertext, is because otherwise, without this value T, an attacker may produce a valid ciphertext just simply multiplying the ciphertext of the keyword W1 with the ciphertext of a keyword W2. Okay, to conclude, so with this scheme, we propose a searchable encryption algorithm that randomizes both ciphertext and trapdoor. And but if we swap the role of trapdoor and ciphertext, it means that also we swap the security level achieved by our scheme. So it means that we can achieve the highest value of security for the ciphertext indistinguishability. Okay, that's the end of my talk. Thank you very much.
Thank you, Irene, for this very nice talk. Unfortunately, we have no time for questions, so I guess you will be happy to receive them privately. And I call to the floor Sigurd Eskeland from Norwegian Computing Center, right? Who will speak about privacy-preserving authentication schemes.
Yeah, here the presentation is. Yes. So my name is Sigurd Eskeland. And I'm with the Norwegian Computing Center, as you just said. And so the title of the paper that I'm going to present is Cryptanalysis of a Privacy-Preserving Authentication Scheme Based on Private Set Intersection. So here's an outline. Basically, there are 3 parts in this presentation. First, I will talk about continuous authentication. So continuous authentication, that is a group of authentication methods that are based on recognizing user-specific features. And such features can be in groups of modalities that are contextual, which means they include location data and IP addresses and such, or it could be behavior, like screen touch patterns, typing patterns, gait patterns, and such. And lastly, physiological modalities like face recognition, fingerprint recognition, and iris recognition and such. So, however, all this has to do with personal information, and revealing such information could cause privacy concerns. So, therefore, there have been proposed several privacy-preserving protocols for continuous authentication. And one such paper was proposed by Domingo Ferrer and et al. I discovered this paper being a supervisor for a PhD student that works in this area. So that's how I discovered this paper. And basically this is a private set intersection protocol that is applied sort of for continuous authentication. And it utilizes pair public key encryption. It assumes a malicious adversarial model, which means that a participant may transmit computations that diverge from the protocols, or from the protocol. So in continuous authentication, we have sort of like 2 rounds or phases. So there is an enrollment phase, and then there is an authentication phase. So in the enrollment phase, there is a user-generated pair public key. However, the user does not generate any private key, so there is no decryptions in this protocol. And the user then samples some user feature template, or in this case S elements, and these are then transmitted, encrypted to the authentication server, which is the other party in this protocol. And essentially, so during authentication, then the user samples also some authentication features, and then these are encrypted, and then there is a comparison based on these encryptions. So by comparing these encryptions, we can see whether or not there are some similarities or dissimilarities in the encrypted plain texts of both the enrollment set and the authentication set. So now I'm going to get more into the details of this scheme, and afterwards I'm going to show that it's not secure in the malicious adversarial model. So first, the user generates a pair public key consisting of 2 elements. So here N is the same as an RSA modulus, so it's a composite modulus. And G is the generator that generates a group of whose order is of the size of N. The user then samples the reference template during this enrollment phase. And we see that these elements of this enrollment template, they correspond to polynomial, and then also to this polynomial's coefficients. And then we observe that for any input b to this polynomial, if then the value of the polynomial equals 0, this means that then this input b is an element of the reference template. So this is sort of the basis of the Domingo-Ferrer scheme. So here are some encryptions. So the user, he then generates this public key, and he generates a number of nonces. So in green here, this is just a standard pair encryption in which these polynomial coefficients are encrypted. So the P's here, these are the polynomial coefficients representing the enrollment reference template. And then also there are some other encryptions denoted R to D, which also contains encryptions of these polynomial coefficients. And then the user transmits all these encryptions to the server and keeps two of these nonces, D and R dash. So sorry about all the details here, but so during the authentication, then the user samples another set of authentication user features, T such integers, and it generates T nonces that are used for encryption. So the server transmits back these encryptions that it received during the enrollment. But also these pair encryptions, they are protected by means of this secret exponent theta that the server generates. So by means of these authentication features, they are then used as exponents in the following encryptions here. And these are then protected also by means of the D exponent and these T exponents. So these encryptions are then transmitted back to the server, which conducts a verification. So we have on top here we have this verification. So it just checks if this expression holds, and if this expression holds, that means that these encryptions, the encrypted authentication features in this round, they exist in the encrypted in the encryptions that was conducted during the enrollment. So that basically means that there is a similarity, but then of course there are T of these sort of triplets, so you have to check for each triplet. And then I have tried to show some correctness and see that some of these factors they eliminate, they cancel each other out. So for example, on the left-hand side of the equal sign here, so I have this slash. This is part of the pair encryption, and this cancels out this other part a little bit further on the right. And the greens, there are still these authentication features that were encrypted during the authentication phase. And then if there is a match, then we end up like we see on the bottom here, because this polynomial, it equals 0, and then you have g to 0, which becomes 1. So that this shows that the expression, this verification, it will hold in that case. Here is the cryptanalysis part. Again, I'm sorry about all the details here. The attacks that I have proposed, so they allow disclosure of both enrollment features and authentication feature elements. And these attacks, they are also undetectable. And again, they apply in the malicious adversary model. And these attacks can be conducted by the authentication server, but also some external eavesdropping, pretending to be the authentication server. Because here there is no actual authentication of the server. So anybody could sort of eavesdrop and then modify the encryptions that are transmitted. So here we see the authentication part of the protocol, and the only modification that I have done here is indicated by red color. So I just multiplied the generated G to one of these pair encryptions, that's all. And then the user conducts the computations following the protocol, which means that we get some exponentiation to this generated G. And then the user transmits back these encryptions to the server. And then by using these triplets that we had here during verification, B and Y and D. So in the case that this B feature agrees with an enrollment feature, which means that this polynomial becomes 0. That means that then everything would sort of eliminate, and we get this product D T disclosed. So these are secret nonces generated by the user. But we can then disclose this product. We are not able to disclose D and T separately, but we get this product here. And this product we can then use in a simple exhaustive search. So we are now just using this this encryption B, and then this protected pair encryption from the authentication phase. And here in red, then we use this this disclosed product that we just got, that we just obtained, and then B hat is just a search variable. And then we can just search and see if this verification, if it holds. So this is a completely feasible search because these features, they are sort of within a limited domain. And if this verification holds, that means that this search variable B hat, that is an element in the enrollment set. So yeah, below I show the correctness. So on the left-hand side, I should mention that all these computations are then done modulo n, but in the original scheme, all the computations are done modulo n squared, like we see here. So when we do computations modulo n, that means that we eliminate or cancel out products containing this generated G. So this gets eliminated. And also there's also another reason for that, because of this product DT, it is obtained within this domain, but while in the original scheme it's I think T's are generated from a larger domain. So, but these details are in the paper. So anyway, this would hold. So now we have been able to disclose the enrollment features, and we can then use these required values from this previous attack in another attack to reveal authentication features Y. And so the asterisk here, it just denotes that these integers or these computations, they have just been acquired from some previous session. So again, I'm sorry about all the details, but here we have again the authentication phase of the protocol. But now we see that the server sends, instead of sending the pair encryption, it just sends a completely different encryption. But still, since all encryptions are sort of random looking, it's not possible to discern and to discover whether or not this is a legitimate encryption or not. And then we see that the user encrypts the sampled authentication feature values using as exponents, and these are then protected with these T nonces. So all encryptions are then transmitted back to the server, and then again the server conducts an exhaustive search. So this looks like this. I've shown the correctness here and see how it sort of adds up. But again, if this verification, if it holds, that means that this search variable is indeed an element in Y in the authentication feature set. So now I'm almost done. So finally I have a few comments, and then there is a suggested way to sort of fix this authentication scheme. So we see that in pair encryption, so the plain text is protected by a secret probabilistic encryption factor. But in this Domingo, Ferreira, and Al scheme, so there is no decryption, and also there is no utilization of this homomorphic property of the pair crypto scheme. So essentially, so this generator G, it doesn't have any function, and this is exactly what is being exploited in these proposed attacks. So the solution is simply just to avoid pair encryption, G has no relevance, and just conduct all computations modulo n. So that means that this G to P factor, it gets eliminated. So simply we just use R to N instead. And using this encryption, if you could call it that, that would sort of prevent both attacks. So I'm sort of quite ahead here on time, but that was all I had. Thank you.
Thank you, thanks a lot. Maybe we have time for a quick question, if any. Okay, if not, let's thank Sigurd again. So last but not least speaker, Elia Onofri from Italian CNR will talk about attribute-based encryption, joint work with Marco Pedicini and Marco Cianfriglia.
Thank you very much for your presentation, Professor Giulietti, and welcome everyone for this last talk of this last session. Thank you for being here still, even if probably you are tired as me. Being most of us tired, I promise I will keep it short and simple. We'll start with some few examples, and then we dive into more details about this work. Today, I'm here to talk about attribute-based encryption in the context of ciphertext policy, and in particular, as the title may suggest, we'll talk about revocable encryption scheme, and this is a work joined with Marco Cianfriglia and Marco Pedicini from the University of Roma 3. And so without further ado, let's move on with the first slide. I think everyone would be familiar with the notion of public key encryption, but please follow me for a little bit. So we have Alice and Bob. Alice has some file, Bob has a public key, and Alice wants to send this file to Bob number 1 at least. And so what does she do is simply to encrypt with the red lock her file and send it to Bob, and Bob will be able to decrypt it. What's the point here? Because everyone else knows this thing, is that we would like to recall that if we have multiple Bobs and multiple files, then we have to encrypt each file with a different key, which is the public key of Bob1 to Bob n. But even if the file is the same, still Alice has to encrypt it multiple times. And so the natural way to think about a model where this situation happens in many times, like in the context where we have some kind of facility, is that if Alice would like to share a file with all of the employees of, for example, of an agency, is simply to encrypt the file with a given kind of key, and then this file is shared among the participants, and then they will be able to decrypt it depending on some features. In particular, in the context of ciphertext policy attribute-based encryption, we use to assign each of the participants in some notion of tag, like it could be, for example, Bob1 is from the IT department, it's a senior and it's from Office A, while Bob2 is from the Human Resources Department, it's a junior Office A, and so on. And then, where's the point here? Is that maybe Alice would like to encrypt the file so that, for example, only junior employees from Office A will be able to decrypt, and so then, at least, hopefully, if everything works fine, is that, for example, here we have Bob2 with the yellow key that can decrypt because he's junior and from Office A, and we have Bob N, which is also junior from Office A, regardless of the fact that one is from HR department and the other is for IT department. So this is more or less the concept of attribute-based encryption that I hope everyone is aware. What's the point then? The point is that we have some criticalities in attribute-based encryption, because let's say if, for example, we have a new employee, we simply create a new key, but what happens if an employee is fired? So someone leaves the company, someone no longer is in possess of his key. Then the first idea that came up to our mind is that simply the server where files are stored will refute to send to the user the file. But we will see in a moment that this is not enough, usually. In particular, there can be multiple instances of situation where similar things happen. For example, someone gets promoted and so gets new right, becomes from junior to senior, then he would like to have new key with new attributes. Or for example, it got downgraded, so it will lose some of the permission he had before. Or for example, least but not last, maybe a key can be compromised or stolen. And so in all of these situations, we would like some way to retain the secrecy of the files. And why this is so important? Because of course, in literature, we have a different kind of approaches to this problem. We call typically revocation problem. And in particular, we have three kinds of revocation approach. A direct revocation, which means that periodically, typically are shared some certificate revocation list or delta certificate revocation list in order to let know people who are no longer in charge of their keys. We can have indirect revocation, where periodically updates a list of valid users and corresponding key. And finally, we have server-aided revocation, which require typically a third-party authority or a third-party server, in some sense, that cooperate for the decryption. And I would like to pinpoint that there is a very important keyword here, which is periodically, Why it is so important? Because this introduces a possible vulnerability, because of course these certificates are shared after some time or at given timestamp in the life of the ciphers. So if we need some solution which are immediate, we cannot rely typically on this notion. And then, so as you can imagine, we are in the last of these 3 points, meaning the server-aided. Of course, I'm not saying that server-aided are not prone to any problem, because of course they are, but at least they provide this notion of immediateness when needed. So, which are the problems here? As I highlighted, there must be, in particular in the direct notion of revocation, a central control, meaning that there is some entity that must share, for example, the certificate revocation list, and this is common indeed for all of the 3 approaches. We have the problem of timing, as we were saying a few moments ago. And a very big problem in indirect solution is that we typically need a key redistribution, because, for example, active user should need a new key after some time, and of course ciphertext re-encryption, because of course if I do not want to avoid I want a user no longer being able to decrypt the file, then I must re-encrypt the ciphertext. And many others, of course. So, before moving into the details, let me present you one more example. And this is a kind of the solution, the problem that drove us into our solution. So let us consider Alice in charge of her file that we like to share. Then a thing that typically happens in reality is that a company wants to hold all of the files on its own private network. But typically what is done is that, for example, they buy some cloud environment from other parties or even other countries, and so the files are not stored locally, are no longer under the direct control of the headquarters of the company, but rather are stored somewhere. And with this somewhere I mean also not only different network, but also a different country potentially, so that is, for example, prone to different privacy rules and stuff like that. So this is something that we must have in mind, because of course when the files are distributed, the company would like to have total control on the server. And so the first question that arises here is how the company can retain the control, and how can enforce, for example, privacy issues with like the GDPR or stuff like that. And so our solution is to have a mediated revocation. What does this mean? It means that when Alice would like to share the file, she put it online on this remote server as usual, so it is completely transparent to her what is happening. But when Bob would like to take back the file, he downloads it from the server, but his green key is no longer capable to decrypt the black lock, because the black lock is no longer associated only with its own attributes, but instead Bob requires the help of a mediator server. What is a mediator server, or security mediator as we refer to it, is simply a third-party authority, which could be also semi-trusted, who is in charge of helping the various parties to decrypt. So Bob sends the black file encrypted to the mediator server, who knows nothing about the file itself, knows only that Bob is the green user. So the security mediator converts, ideally, the file from a black lock to a green lock. And then, of course, Bob has a green key, so he is able to decrypt the file and have access. But the point here is that since the security mediator is under the direct control, in some sense, of the central, of the main headquarters of the office, then of the agency, then the agency still have control. Access control over who can access the file stored into the remote cloud. Okay, back to public key encryption. I found recently this very interesting work called RSA. Probably someone of you knows about it. Just joking. I don't think there is necessary to explain anything about this, but let's just say that I recall you that there is a public key composed by N, which is the product of 2 prime. The secret key is simply a decryption exponent related to the encryption exponent of the public key, and then this is the encryption decryption. Why am I bothering you with this thing? Simply because in 2001, Bonnet et al. Proposed a mediated version of the RSA in a very interesting paper called The Method for Fast Revocation of Public Key Certificate and Security Capabilities. And the idea here was that the public key is the same and the secret key instead is not. Why? Because the real secret key is something of, we can say, ethereal, meaning that no one possesses the entire key, but rather the secret key is divided into two pieces or more pieces eventually. One is given to this security mediator and the other is given to the user, with the interesting property that the part of the key which is given to the security mediator is uniformly at random. I missed, sorry, a U here for uniformly at random in Z phi n star, meaning without 0. So actually the security mediator has no information at all about the key because it's a completely random value, and of course neither Bob, the eventual Bob, the user, is in possession of any information about the ethereal key because of course a given number minus a random number is a random number as well. And so the encryption is the same, so again it is transparent with respect to Alice who would like to encrypt the file, while the user can decrypt only with the help of security mediator because, of course, he needs a partial decryption, which is y elevate exponents to the decryption exponent of the security mediator, and then the total decryption happens as well, and you can simply check that this is correct as I show on screen. Okay, so why I present this result from Bonnet? Because a natural extension of public key encryption is the identity-based encryption, as we can see in the paper by Sahai and Waters from 2005, and then identity-based encryption naturally extends to attribute-based encryption, as we know. And in particular, we, of course, focus on ciphertext policy attribute-based encryption, as I was saying, and I would like to just quote the paper by Betancourt, Sahai and Waters, which was the first ciphertext policy attribute-based encryption paper who presented a model. And in particular, I would like to recall you that most of these kind of ciphertext is based on pairings and bilinear maps, which is the problem with pairings and bilinear maps. Problem called Shore, which ensure that probably in a few years all of these kind of cipher will no longer be useful because, of course, while quantum computers are next door, we all fear that problem like discrete logarithm factorization and other stuff will be broken in a few time. So we proposed, we analyzed the various ciphertext policy attribute-based encryption method, and in particular we found a viable one on the one proposed by Zhang and Zhang in 2011, in particular because it is based on lattice problem with the LWE problem. And so sorry, and so we worked on this framework to extend it to with the security mediators idea. So, what is more formally ciphertext policy attribute-based encryption? And I think that these are not the last version of the slide. So there will be a few typos I will pinpoint. The idea is that we have a setup algorithm which takes sigma, which are security parameters, and R, which is an admissible set of attributes. We will see in a moment what these attributes are. And what this setup algorithm does is to output a master secret key and the public key. Now, here we talk about the master secret key because, of course, it is something that belongs to the owner, in some sense, of the encryption scheme, the one who will provide keys to the user. So in our example, the agency, for example. Then we have a key generation algorithm that takes the master secret key and a set of attributes and produces a secret key for a given user with those set of attributes, of course. We have an encryption function which requires, of course, the public key, W, which is an access structure for a ciphertext, so it specifies which kind of user can access that given ciphertext, and of course the message M, and produces the ciphertext C, and then at the end we have the decryption function, which requires the secret key of a user and the ciphertext, and as well as far as the the user have an attribute set which is valid with respect to the access structure, then it should output the original message, otherwise it should do nothing, or at least hopefully won't learn anything. So let's dive into the details of Zhang Zhang's method for attribute-based encryption with a brief overview. So the idea here is that we have lattice parameters n and m, which are the sides of the lattice base, and the modulus q, and we have a basis which is nearly uniformly at random on zq to the power of n by m, so it's a matrix in zq of that size. And then the message encryption is performed in LWE manner, meaning that it's like the method proposed by Gentry-Packard and Gentry-Packard et al. in 2008. Sorry. So the idea here is that we give a random secret assigned to the ciphertext, which is uniformly at random again, and the ciphertext payload is then evaluated as an LWE sample with the addition, of course, of the message itself. And for any one of you that attend this morning session at the 9th floor, we talked a little bit about these topics. Otherwise, I hope anyone can follow me. Otherwise, please ask me. And where's the point here? Here, S is the secret which hide the message, and it is hidden as well in a Shamil secret sharing fashion, meaning that the attribute, in some sense, contribute to the retrieval of the secret itself. Ideally, just imagine like in a secret Shamil secret sharing way. So here, users are provided with the fixed attribute, say 0, plus R cardinality of R attributes. So each user hold all of the attributes, which can be given both in a positive or in a negative way. Meaning that for each I in R, we can have, say, I plus the positive attributes and I minus the negative attributes, and this form a partition of the entire set of attributes, while access structure inside the ciphertext are specify both positive or negative, or either both. So in this case, the positive plus the negative attributes associated to a ciphertext are not partition, but rather two covering. And then we just say that S satisfy V if the positive attributes of the user belongs to the positive attributes of the ciphertext, and the negative attributes of the user belongs to the negative attributes of the ciphertext. So, very briefly, I'm not assuming that all of you understand everything it's written in the following algorithm, and I refer to the complete paper that will be published, as Professor Sala said, on Journal of Mathematical Cryptology later this year, the beginning of next year. But you can also find an early version on ePrint, is number 922 if I remember well. And in particular, so the setup here is simply, let's say simply, the generation of a basis for the lattice B and a related short basis from the orthogonal lattices, and in particular it is used the well-known trapgen function from, if I don't get wrong, Gentry, Packard and Vancouver trapdoor for hard lattice and the new cryptography construction. And apart from this, the main idea here is that simply if you are into the lattice problem, this matrix B and this matrix B describe the same lattice, but the matrix in red, which is the secret key, the master secret key, does it in a way where we can perform computation simpler. Then the point of the rest of the key is simply to generate one matrix for each possible positive attribute, and one matrix for each positive negative attribute, and then to sample a vector U, which will be our 0 point, as I was saying before, that will be related to the matrix associated to the lattice. Then the key gen for a user is simply to take all the matrices associated to the correct attribute the user has, meaning that if a user has a positive attribute, then we take BI plus, otherwise we take BI minus. We concatenate all of them, and then we extract an a solution for a generative sample element from the lattice, meaning an element from the discrete Gaussian that satisfies this relation. Okay, and in particular, this can be done very efficiently with this algorithm called Gen sample pre, which is an evolution of the classical sample pre introduced by Gentry in 2009, and this one can be found in the paper by Alwan, Packard, by Kash, Hofstein, and Kiltz. The reference will be at the end of the slide. Originally, the correct version of the slide had the reference here. Sorry, and then. How do we perform encryption? We simply build an LWE sample per each element involved in the computation. Namely, for each matrix associated to the attributes we would like to make the user able to decrypt, we build an LWE sample. We build an LWE sample for the 0 attribute, which is our 0 point there later in the Shamil secret sharing approach, and we build an LWE public key encryption element from, of course, our element U that was the one we generated in the setup phase. And why this is so important? Because this way in Z we have the payload, so the message, while we are hiding S, which will later be retrieved as the 0 point of the other elements in some sense. Hopefully it will be clear looking at the last algorithm, which is the decryption. So here simply the user retrieve all the correct CI from the ciphertext, and then perform this multiplication, which is private key multiplied by Y, and this in particular is, as you can see here, simply UTS plus some error, which is the agglomerative of all the LWE error. and then he is able to evaluate Z as simply, M as simply Z minus A, and then this is a classical LWE PKE approach. Then, how do we perform our mediated scheme? And I promise there are only a few more slides before going home. So the setup phase is the same as the regular scheme. Conversely, in the key generation, as we saw in Bonnet approach, we built the mediated key generation that outputs, apart from the secret user key, also some mediator key. Why I say some? Because of course I presented it with a simple single mediator key, but with the same approach we can divide the secret amongst multiple mediators. Then the encryption phase is the same as in the regular scheme, as we said that this approach is completely transparent to the data owner that wish to encrypt their data. And then we have two more functions, which are partial decryption and mediated decryption. Mediated decryption is run by the user who would like to decrypt with the aid of the security mediator, which runs instead the partial decryption algorithm. And so, as I was saying, the setup and encryption are the same as regular scheme. So here, parameter structure is the same as the regular scheme, or indeed very similar, with just a few changes, but asymptotically they are the same. Encryption is not modified, so the algorithm is transparent. And analogously to Bonnet et al., where the mediator key is uniformly random, also here the mediator key is uniformly random, so it holds all the good property that we introduced before. And in particular, as I was saying, we can consider up to k security mediators, and so the main issue here is the overhead during the key generation, because instead of generating a single key, we have to generate k plus 1 actually. And okay, so let's go again to the algorithm. But before that, I should say that as far as a single element inside all this set of user plus security mediator is honest, the scheme is totally secure. So the setup is the same, so I won't report it here, but the key gen is very similar to the approach by Bonnet, because we evaluate as a uniformly at random the keys for the security media for the user. So this is the virtual key that will be held by no one. Then we generate for each security mediator a single key, and then we evaluate the user final key as u minus the sum of this key. So here again, the main overhead is that this algorithm gen sample pre is quite heavy and must be run once per each mediator. Then the encryption is the same as before, while the partial decryption is simply the multiplication of mk by the ciphertext y. However, here we have to add another LWE sample, another LWE error. Why? Because in this way we can protect the mediator key from the user, so that the user cannot stole the mediator key by inverting that relation. And here is the complete decryption of by the user, which simply firstly retrieve y as before, evaluates this A, which is no longer the complete A, but is rather an A0 belonging to Bob, and asks even asynchronously to the various security mediator for their partial secret, in some sense, which can be then simply summed together, and at the end we end up with the same decryption as before. Okay, so with no claim of completeness, I can only give you the formal definition of the security model. So with these parameters that are shown on screen that I I've not time today to comment. We have proved that the entire mediated scheme is as hard as the LWE problem. So as far as no lattice problem are broken, we are still in a post-quantum environment. And in particular, we have proven with the classical selective chosen plain text game the security of the scheme itself. And so this means that as far as exists an adversary A that breaks the selective chosen plain text attack security for this scheme, then there is an adversary that solves LWE. In particular, we cannot only rely on the security from an external point of view, of course, because since we are in a mediated environment, then we have to also take care of the possible collusion between users and between servers and between users and servers. So in the complete version of the manuscript, there are also the proof for the following threats, which is a user is not able to decrypt as far as at least one security mediator is honest. This means that even if you have k-1 security mediators that are colluding, then nothing can be learned. A user cannot reject a revocation in polynomial time, meaning that even if he has gotten a lot of correct decryption, if it is revoked, then he cannot break or forge the security mediator's key. And of course, as in regular ciphertext policy attribute-based encryption, multiple users cannot collude to retrieve any information of the message. And in particular, also the same holds for the side of security mediators, meaning that one or more security mediators cannot collude among themselves and cannot retrieve neither the user's secret. So, finally, just to conclude, we have not only provided the formal proof of security in the case I said before, but we also implemented the scheme on Palisade Abe library, which is a well-known crypto scheme in the context. It's an open source, and they provided the base implementation for Zhang scheme. So we extended in order to provide a practical proof of the work of the scheme and an efficiency statement. And in particular, as you can see, there are big issues with the performances, meaning that if the decryption takes a few milliseconds, the partial decryption plus the mediated decryption takes way more. But why this is true? This is true because we cannot compare directly the decryption with the mediated decryption, since the mediated decryption holds inside, hidden, of course, in the partial decryption, another encryption by the security mediators to hide their key. As we said before, we use still an LWE sample. Sorry, I got back just a few slides. Here we are generating this LWE sample, and the problem is that all of the computational burden is related to the sample of this Gaussian error. And so what we can say here, we can say that as far as this is the model, these are the best performance we can obtain. But the very interesting fact is that since the queries to the security mediators can be performed asynchronously, then even in the case of 1,000 security mediators involved, then the time will be the same. And well, these results are then commented for 10 to the 5 bits of encryption and one security mediator, but they holds for any key. So, final remarks, just to conclude. We have proposed the first revocable ciphertext policy attribute-based encryption on lattice, hence being embedded, as we said, in a post-quantum secure environment. We implemented it on Palisade open source library, and we have provided both the correctness from an experimental and a formal point of view. And which are the points for the future? Well, of course, as I was saying, we can adopt multiple security mediators instead of one, but we can think also of a different topology in the security mediator scheme, meaning that, for example, to reduce the burden, the computational burden of the security mediators, we can think of distribute the secrets amongst the multiple security mediators, and in particular we can also think about a threshold scheme in order to avoid like denial of service attacks on security mediators. We plan to extend the approach to a multi-valued attributes encryption scheme proposed by Zhang and Jie a few years afterwards, and also to ring LWE extension. And in particular, we also plan to support to other libraries like PyFL and others the support of this scheme in order to be tested out more efficiently. So just to give you, these are the bibliography I have quoted on my website, which is eliaonofi.it. You can find the complete version of the slides with all the details. So thank you for the attention, and if there are any questions, you can contact me.
Thank you, Elia, for this very detailed...
And I was on time yet.
Yeah, just right, for this detailed talk, and thanks all the speakers of the session. And I give the floor to our president for closing the Congress.
Well, what to say? You are a lot. You resisted till the end. So it's been a very nice event. I'm very happy. And next will be at the end of September. And this time we'll be hosting Bank of Italy, Banca d'Italia. And so we are planning an even bigger event, larger rooms, more people. I think it will be super cool. So see you next year.